All right, chemistry. This is our first in our three-part series on acids and bases. Our goal here is that we're going to kind of go over today talking a little bit about the differences between acids and bases and how pH is calculated. In our part 2 video, we'll look at the various types of reactions that happen when we look at acids and bases. And then in our last one, we'll look at how stoichiometry fits into this and this stuff called titrations. So that's going to be kind of our series of what we're going to do. When we first start looking at acids and bases, I always like to look at water first. So really what we're going to do is we're going to look at the case for water and what happens with it. Now typically we say that water doesn't like to separate into ions, but at a very, very weak level it will dissociate into ions. So we actually show two arrows going this way and that way because water will transfer between these ions and the actual molecule water. So when I look at this, I usually look at it and say it's going to form a hydrogen ion and it's going to form a hydroxide ion. Now these are the two ions that kind of represent whether something is going to be an acid or whether something's going to be a base. So usually what we do is we look at the hydrogen ions and we say, well, what's going to be our characteristics about that hydrogen ion? Now, if you think about it, a hydrogen ion, so if we had like an atom of hydrogen, we'd have our nucleus, which would have one proton, and then we'd have our one electron. And if we want to make this into an ion, that electron would have to leave, okay? So we lose our negative piece, so the only thing that's left is that positive proton. So when we write this, a hydrogen ion is really nothing more than just a proton, okay, that we see kind of floating around. Now, generally that proton is never going to be by itself, so what we do is we attach it to another water molecule, and when we see that put together, that's what makes this thing that we call the hydronium ion. So an H3O+. So this is called hydronium. And that's the ion that we generally associate with acids. Now again, you could see it written like this, or you can see it written like this, but both of those are the things that make things an acid. Now when we look at things and we say, well, what about being a base? A base is something that we'll see as this hydroxide. So any hydroxide that is attached in a compound will make something a base. So this is a base indicator. Now really what I look at is I say it's anything that has the ability to attach a proton to it. Okay, so this is any proton acceptors. So anything that's classified as a proton acceptor could potentially create a base. So what are some other examples of things that would be proton acceptors? Well, we always like to see things like carbonates. So a carbonate is a proton acceptor. It could go ahead and grab a hold of some of these. In fact, when we add some hydrogen to it, we're making something that makes it an acid. So we like to start to see things as anytime we have acid or hydrogen attached to something, it's going to be a acid. Here's another one is our bicarbonates. So if we have a bicarbonate in solution, it's going to be a solution that will be basic. Anything that has a chloride or any other halogen could be a proton accepting solution, which means that it would also be a base. So really these are kind of the ones that we'll probably see most often. And that means that if we wanted to, we can make acids by always adding hydrogen to the compound that, or a solution that has these proton acceptors. So generally what we see when we look at acids, they come in two categories. They're binary acids And the word binary, meaning 2, is an example of when we take, say, hydrogen and we attach it. So here's a hydrogen that's going to be attached to our chlorine. So this is going to make a hydrochloric acid. And so anytime we have a single proton accepting type anion and we attach a hydrogen to it, we created a binary acid. Now the other type of acids that we have would be a oxyacid. Now an oxyacid uses some of the other proton acceptors. So again, any of our proton acceptors are all of our polyatomic ions. So in other words, all of these polyatomic ions could create an acid because they all have the ability to accept that proton. So like our common one, a real common one would be acetic acid. That would be our C2H3O2. So C2H3O2 has a negative charge. Well, if we add one hydrogen to it, we just made an acid, and this is what we call acetic acid. Acetic acid is also known as vinegar, so that would be an example of making some vinegar. So we could do one other example here. I'm going to go with let's look at another one here. Oh, I'm going to do the sulfuric acid, because we've seen that already. So if we take our sulfate, SO4, which is a -2, and we add the hydrogens to it, okay, so we are donating protons to this, we just made sulfuric acid. So this is kind of the different types of acids that we see. Now when we start to talk about characteristics, like what makes an acid, generally what we see is that proton is the ability to have that single proton that can be donated. So proton donation. We see this in our everyday life, though, as something that maybe has a sour taste. So a sour taste, something like lemons, limes, they all contain citric acid. The warheads, any of those are containing that type of an acid. Vinegar is also a very sour taste to it. So these are things that would make it an acid. If we see that the pH is less than 7, then we know that we're dealing with something that's on the acid level. If we look at it in terms of indicators, okay, so there are indicators that will shift one direction or another. So we'll talk about indicators, but anything that kind of turns like a red litmus blue would be an acid. Okay, so excuse me. Well, just be an indicator shift. I don't have that one right off the top of my head, but I'll double check it later when we talk about indicators. So sour taste and pH less than 7. So that's usually something that we look at when we see something that's acidic. And these are in a lot of the foods that we eat. Okay, so these are a lot in the foods that we eat. When we look at our bases, though, base properties are more bitter to taste. And we don't eat a lot of these. The bitterness is what actually keeps us away from things. So a lot of this is something like soaps, detergents, okay, those are things that are going to be much more on that basic range. A good example of another one would be when we have that hydroxide to it, would be like a sodium hydroxide. So if we had an NaOH, okay, sodium hydroxide is usually used in our drain cleaners, so that's a good example of a base. And when we dump it into water, it creates that hydroxide floating around where really the sodium is just a spectator ion. We also see these whenever our pH is greater than 7. So whenever the pH becomes greater than 7, then these are things that are going to be on that basic level. Okay? When we look at pH, okay, I want to go back and just talk a little bit about our pH scale and where pH comes from. Okay, so the pH of a situation ranges usually from 0 to 14. Okay, now it doesn't mean that we can't go lower than 0. In fact, a lot of times we could, but it's about a concentration issue. And it's not that we couldn't go higher than 14. It's just that we see most of our situations lie in that range of 0 to 14. Now, pH is something that depends upon concentration. So concentration is the key here to talking about pH. And when we talk about concentration, we're talking about our molarity. So, for example, in our water situation, our water dissociated to form hydrogen ions and hydroxide ions. And really what we're looking at is what are the concentrations of these. And we usually see them as 1 times 10 to the negative 7th molarity and 1 times 10 to the negative 7th molarity. Now what this means is that we're in that range that's generally neutral. So we see this as something that would have a pH of 7. Because our concentration of our hydrogen ions is at that times 10 to the negative 7. Now when we look at how do we calculate pH, pH is a logarithmic thing. So it's the negative log of whatever the hydrogen ion concentration is. It kind of goes back to like why do we do a lowercase p and an uppercase h? The h is representing that hydrogen ions. And so it's the power kind of the hydrogen ion in the solution to kind of give us an indication of what's happening to it, whether it's going to be more acidic or more basic. So like if I go through and I did the negative log of 1 times 10 to the negative 7, I'd be able to figure out what my pH is. Now this is going to require you to kind of do a little bit of work with your calculator. So we're going to have to make sure that we're in a scientific notation or a scientific setting so that if I do the, let's see, I'm going to do the 1 EE7 negative. So this is going to give me my concentration. So that's the same as 1 times 10 to the negative 7th. And then I'm going to take the log of this. Okay, so log of that, and then I got to put a negative in front. So the log of this is 7, so our pH is really 7. So that's what gets us to the basic level. And that's why we say water is generally in the middle, and it's a slight shift on what we do to these, in order to see where we're going to go. Okay. Now, if we wanted to do, say, figure out the pH of a different solution. So let's go back to one of our solutions that we were dealing with before. Let's deal with some hydrochloric acid. Okay, so I've got some hydrochloric acid. Now, when that is added to water, so in other words, if we have an aqueous solution of hydrochloric acid, we know that it's going to have hydrogen ions that are going to be aqueous in solution, and that we're going to get some chlorine ions that are going to be aqueous in solution. So we're actually getting that concentration to float around. And again, we might see this like this, but really these things are attaching to a water molecule, so we get H3O plus ions. But remember, these are equivalents to each other. So we usually like to look at the dissociation of our acid. So like our hydrochloric acid, when it dissociates, is going to form a 1-to-1 ratio with the hydrogen ions in concentration. So if we know the concentration of the hydrochloric acid, let's say we have a 0.25 molar solution, then we know that this is going to be a same concentration because it's a 1-to-1 ratio. Now that we know our concentration, we can figure out our pH. So pH is just equal to the negative log of whatever that hydrogen ion concentration is. And we use brackets around it to kind of indicate that we're talking molarity here. So I'm going to go ahead and do my calculation of this. Okay. So we've got our 0.25. We're going to take the log of that and then take the negative of that. And you can see here's one where we ended up with a pH that actually is pretty low. So 0.60 is our pH. And that's definitely in that range that's going to give us something that's an acid. Now generally we probably would never see a lot of acids that would be in that range, and so what we would tend to do is we would look at something and say, well, maybe we know the pH of something, so maybe we're given the pH. Let's go and look at a different type of an acid, so like acetic acid, for instance. So like C2H3O2. This is that vinegar that we had earlier. And if we look at this, this one doesn't dissociate completely. So this is going to be a key indication of the difference between types of acids. This one, when it dissociates, is going to form some hydrogen ions, and it's going to form those acetate ions. And they're going to be aqueous in our solution. And we have an aqueous solution of acetic acid. Now the problem is that not all of it transforms into this. So maybe we have something that's going to have a pH. So we know, so we might be given that the pH of our solution is equal to, 5.4. So we have a vinegar solution that's at a 5.4. So let's go ahead and we can figure out what the concentration is of that hydronium ion, or that hydrogen ion. So then what we'll do is we'll undo our log function. So really we're going to do the 10 to the negative pH is equal to our hydrogen ion concentration. Now I wrote it as the hydronium ion, but remember that's the same thing. So if we did this with our math here, 10 to the negative 5.4, we can figure out what that concentration is. So again, we're back to our calculator. Okay, and there's our 10 to the, so we're going to go 5.4, make that a negative, hit the 10 and so we can see that we are at a concentration of 3.4.0 times 10 to the 1, 2, 3, 4, 5, 6. Negative 6. Okay, so we got 4.0 times 4 times 10 to the negative 6 would be our concentration. I just want to double check to make sure I got that. So 5.4 negative 10. Yep. So that's how we would figure out that concentration. So that's the concentration of that hydrogen ions. There is a chart on your green sheet, okay, that's going to help us kind of maneuver around through all of this work with pH. So you can see that we've got our list of our equivalences here. So for instance, to find the pH of something, it's the negative log of the hydronium ion. And to find the concentration, it's just times 10 to the negative pH. And so these are where we could start with, if I know the concentration, I could find the pH. If I know the pH, I could find the concentration. So really we're kind of looking at just going between these two areas. Let's do one last thing. We want to talk a little bit about the what happens if we have a base. So we know that bases are those things that would have hydroxide, for instance. So I'm going to just go to my NaOH and say I have an aqueous solution of it. Well, when this thing dissociates, it forms our sodium ions and it forms our hydroxide ions. And again, this one is going to be a strong base because it's going to dissociate fully. Okay, so the differences between something that dissociates as strong would be something like the hydrochloric acid is a strong acid. Because it dissociates fully, where the acetic acid was a weak acid because it didn't dissociate fully. It has the ability to kind of bounce between, and that's again water's ability to switch between the two. So we kind of show the differences in the dissociation of weak versus strong. So when we look at something like this, this is going to be a 1-to-1 ratio. So in other words, the concentration here, whatever our molarity is here, will be the same molarity here because it's a 1-to-1 ratio and because it's a strong situation. So let's say we have a concentration of, let's go with 3.5 times 10 to the negative third molarity. So that's the molarity of our base. That means that our hydroxide will be the same, but what we're really looking for is what's the pH of this solution. So we're trying to figure out the pH. Now we have this thing that's called pOH. Okay, and pOH is similar to pH in that it's the negative log of, now it's the hydroxide ion concentration. So it's just going to find out how strong is the hydroxide in the solution. Now what that does is it gives us another branch on our table here so we can go between these two. There's our pOH and there's our pH, and the math works the exact same. And then to bridge between the two, we just know that the pH of a solution plus the pOH of the same solution will equal 14. So in other words, that ties us back into how we can get between the two. So what I'm going to do here is I'm going to go ahead and find my pOH first. So I'm going to find the pOH of our solution by taking the negative log of our concentration, so 3.5 times 10 to the negative third. And we'll set that up on our calculator to figure out what our pOH is. Alright, so we've got our 3.5 to the negative third. There's our concentration. And we're going to do a log of this. And we're going to use the negative. So this came out to be a pOH of 2.5. Okay. Now, when we go through and we find our pH, pH is just equal to 14 minus the pOH. So, if I take my 14 minus my 2.5, that'll give us 11.5, and so that gives us a pH that puts us in the range of what we'd expect for a base. So, just to kind of make sure that you kind of remember, when we look at our acids and bases, we're looking at things that are going to be hydrogen producers or donators and proton acceptors. And so these are all of our anions that like to do that. And that pH is going to tell us to where we're at, whether we're acids and bases. And so you'll use your green sheet to make sure that you kind of set those up. And we'll look more at this in the part 2 video.